how this modified gravity theory came into the picture, and how this cosmological model again you can restructure and reform in frame of modified gravity theory, right? So coming to the first part, what is relativity and cosmology? So all of you are familiar with the Einstein. So everyone knew Einstein, Newton. So these are the what you can say pillar of the physics or pillar of the physical science, we can say. And they are not only physicists, they are also belongs to mathematics family. So general relativity, which is introduced by Albert Einstein in 1916. Okay. So initially it was first Newtonian theory. After that, again Einstein come with the new theory where the matter and space-time geometry and matter of the universe combine. So that is what the general theory of relativity stands for. And general theory of relativity that gives the basis of disciplines of cosmology. What is cosmology? Cosmology is the structure and origin of the universe on the large scales. So basically, it is a branch of the physics, or you can say physical science, where we need to deal with the study of physical origin, evolution of the universe. And another part also general relativity forms or deals with the relativistic astrophysics. That means the study of galaxies, quasars, neutron stars, and so other etc. astrophysical objects and all. So if we define the whole structure, the relativity, cosmology, physics in a simple way, we are traveling in a train, right? So if we take the whole train is cosmology or cosmos, if you discuss about the whole train, that is cosmology. If you are particularly fixing one birth, then that will come to the astrophysics. And if you are particularly studying the each object on that birth, that will be your astrophysics, or you can say the star, neutron star, and each object if you are studying. So that is how in overall layman picture you can say. So now here mathematically we want to observe the evolution of universe. That is what the cosmological model stands for. And now usually in cosmological model, in the framework of GR or in the framework of modified gravity, what exactly we are doing in that? So usually we are solving the Einstein field equations and governing field equations of the evolution of entire universe. And what are the possible uh, properties or dynamical properties and so on, that we will just discuss. So this is per scale the universe behaves is homogeneous and isotropic. So that for the simple mathematical definition can represent that phenomena. So now point is, what is homogeneous and what is isotropic? So homogeneous isotropic means if the it is a property, homogeneity is a property that the universe looks identical at every point in space. If I can give one example, when you are looking into the sky uh, at a night, if we see the moon is near our house, and if you are going to our friend's house, there also you can see the same moon. Okay. In that constant, if you see homogeneity stands for, it will be looks identical at every point. And similarly, isotropy in that context, it looks same in every direction. That is what I say. In every direction means from my house and from my friend's house, the moon looks same, and the size of moon does not changes. So that is how we can picturize how the homogeneity and isotropy behaves. And this is at the large scale. Now, so initially it came when the special relativity, general relativity, and all those things came. So first, the relativity principle has no idea about what these things and all. Again, the special relativity come when they enter the time component into that. Then the GR, it will completely genuinely new idea came into the matter and space time together. And then coming to the implication of cosmology. Okay. So before going to this implication of cosmology, and we are dealing with the mathematical formulations. So we must know few vocabulary or few terms, which is, we can say, the cosmological parameter or cosmological structure of a mathematical model to study the evolution of the universe. So the first component in that case is known as curved space-time. So general relativity implies space-time is curved in the presence of matter. Since the universe contains matter, so might expect overall curvature as well as the local gravity wells. So now the question is, what is this space-time? Okay. So what is this space-time? We must know what is space, and then again we are including the time into this. Now, so when we are dealing with general relativity, basically this general relativity, which is a geometric theory of gravitation, we can say the geometric theory of gravitation, and it generalizes the special relativity and Newton's law of universal gravitations. Okay, so what it defines? It defines that the curvature of space-time is directly related to the energy and momentum, the part. So now the thing is, what is this space-time? Because that is the key point or key, what is that, key of the general relativity. So what is this space-time? In mathematical model that fuses the three dimensions of space and one dimension of time into a single four-dimensional frame. That is what known as your space-time. So let's see here. In space, basically we are taking, if space coordinate, let's say x, y, z. Okay, and then if you are taking the time coordinate, let's say t. So if you are taking all this time coordinate and space coordinate together, then we will say it is space time. Okay, so how it behaves, how we can study the space and time, both have different units, how we can do it together. So basically, when you are dealing with this general relativity, or we can say in a, and this, see, this thing is four dimensional structure, or we can say it is four dimensional coordinate. So whenever we are dealing any point in this coordinate, so basically when we are dealing with the space, this is how a point is there. Now if you are implementing the time component into that, then this point, it will be known as the event. Okay, so a point in space time is called event, and it requires the four numbers to be specified, and the three dimensional location in space plus position in time. Okay, so the thing is, I came from here how this curved space time. Okay, how this curved space time came into the picture. So now we are taking this space coordinate, three dimensional space coordinate, and along with the time coordinate. And now if we are dealing a point on space with respect to time, then we'll say it is a event. Okay, and it can be represented with this four coordinate structure. And an event is represented by the set of coordinates, let's say x, y, z, t. That is what I told. So that's why the four space time is four dimensional structure. Now, again, the thing is, how the mathematics helps in defining this relativity and cosmology to study the evolution of universe. First I told that curved space time. So the thing is, from where these things is coming, the idea is coming from this space time or curvature. All these things are coming from the differential geometry, which is nothing but one part of our mathematics, which is wide applications in this area. Okay, so this space time, curvature, and all those things, it is coming from this differential geometry. And each term, this cosmological or relativistic term, it can be represents through a tensor. Tensor is nothing but and then the next one is tensor. Okay, so vector quantity is also a tensor with rank 2, or I think like that. So, and also Lie algebra, where the defining the space-time metric, and then the Einstein governing equation, that is from the differential geometry, and then the equation. And if you are going to study the observational consequence, that we can use the statistics. And again, if you want to know the approximate or approaching solutions, then we can go for the numerical simulations. So in general, if you see that cosmology or relativity, which is nothing but this is just physical expressions or theoretical expression representations of these mathematical structures. So if we are constructing a model using this mathematics, then the model behavior will give the output which will represents the evolution of universe or objects into that. Okay. So if you see here why the cosmology relativity is a part of applied mathematics, so this is the reason why we say it is a part of mathematics, applied mathematics. So these mathematics subjects are applied into that to study those things. Now I came to the curved space-time, what we are discussing. So first we should understand how this space-time, how this equation is getting, how this equation coming into the picture. Okay. So let's come to here. Okay. So when you are taking a distance between 2 points, let's say in 2D, if you are taking 2 points distance, so how you are taking the distance? Usually we can write a 2 point distance. Let's say this is x1, y1, and another one is x2, y2. How to find the distance between those 2 points? So we can use to take x2 minus x1, y2 minus y1, and how the distance formula is x2 minus x1 square plus y2 minus y1 square. In general, if we say the distance between these 2 points, let's say you can write dx square plus dy square. This is the distance in two space. Similarly, if we add in three-dimensional, then we will add these things. Okay. Now, here in space time, the space time, what we are taking the same distance. Okay. So we are combining two distance. Suppose we have a point, let's say in our space time coordinate. So what we will do, how the difference between these 2 points with respect to space, and how the difference between those 2 points with respect to time. So the combined those space known as the space time interval, and that space time interval is represented mathematically, which is known as this space time, or we can say, and this known as the line element, or we can say space time metric. Okay. So and that metric we can take in Cartesian coordinate, spherical coordinate, and it has so many references. So I just want to make you clear a little bit. There will be a question space, the things and the distance between space, it will be measured by the kilometers and all. And again, distance with respect to time, that will be measured in the another units like second or minutes and all. Then how we can take the together things? So to take this space time interval means the difference between those two events with respect to space and the difference between two events with respect to time, combinedly it is known as space time interval, and it is governed by a scale factor, or we can say the speed of light. Okay. So then all together we can write, if you write, let's say ds square, the difference with respect to, let's say this is our dt square and minus the x square, y square, z square, these things. Okay. So the thing is, here we have to put the factor or speed of light, which connect the time and space. That means which will convert the units of time in kilometer, and then combinedly it will take. Okay. And then all together, if you take, and the whole variations or whole observations, if it with respect to the light, then these things it will vanish. So that is how it will came into the picture, how the space time is came. So in general we can write ds square equals to c dt square minus dx square minus dy square minus dz square. So this is the space-time interval, or in mathematically, while we are going to do the cosmological model, we are treating it as a space-time metric. And the factor where it is speed of light has to be there, which connect those two things. Now coming here, so the thing, 1 minute. And this square, which is the measure of the separation of events with respect to space and along with respect to time together. Okay. Now, so here, if you see, this is a two-dimensional curved space. So here we have taken the coordinate in radial coordinate, which is r theta 4. So if you are taking the point r theta and let's say this is another point, then how the space-time interval is occurs here. That means, and what are the terms that is given the things. Okay. So now, so this is in 2D space time. Now coming to the 3D space time. So 3D space time, when will come and when will define that space time interval. Okay. So the space time interval, it is same, we will take it and along with r theta and z. So when you are coming to 3D, let's say spherical coordinate. So in that spherical coordinate, we will get this metric. Okay. So I just want to go to the brief like history of these things. It is the advanced one. Let's say yeah. So when I describe the geometry of any space in terms of metric, that is what I said, when it is in Euclidean metric, means a flat space. Now if you change into the code, now you let's say we'll change the coordinates, then we'll get this kind of things, and now the space time or the things it will convert to in this way. Okay. So now, so when we'll add the curvature into it, and then the space-time matrix, it will vary, and then when you will have negative curvature, then the space-time matrix and the space-time interval will differ like this. So in general, when you will reach here, then we will get this kind of things. So here the same things we have represented when you have saddle point, when you will open, and when you will get the negative curvatures, and how the things it will vary from like how the space-time will define the structure of the universe. Okay. So here the thing is, as I said, this is your speed of light which connects these things to these things. And now there will be a question, this term, where this term is coming. I'll come into that part. This metric, when you are claiming that our universe is expanding. Okay. So when the universe is expanding, and that will be discovered by the Edwin Hubble in then after that the space-time matrix has this term which is known as the scale factor and which represents the expansion rate of the universe. So that's why this came into the picture. So I'll say how these things is coming into the picture when we will go for the Hubble's law description. So as I told, this is when you are dealing with the relativity cosmology and the cosmological model and mathematics background. So these things is the main key components of this cosmological model. And in this matrix, when you will say the co-moving coordinate, so there will be a question, what is this co-moving coordinate? So when we are observing one event, and if they are changing the one place to another place, that is then whole frame it will go from one to another. So co-moving coordinate, they will not change overall expansion. It's like if you are putting one dot in a balloon and you are blowing that balloon. Okay. So what will happen? It will, the surface will expand, but the dot point, it will not change the it will be unchanged overall the expansion or contraction. That is what the co-moving coordinate concepts coming into the picture. Now coming to this curvature, how the and so on, and then this defining the proper distance, that is also needed while going for the cosmological model. So how we will do? how the proper distance is getting calculated. It is basically the origin and the object are the coordinate. So that will give you the proper distance, and then from that proper distance, when it will that will be derived from this term which is known as the curvature term. I'll come to that. And now how these things it is getting defined. And another one is very important when we are dealing with respect to the light travel, or when the light changes and all, then we will come to the cosmological redshift. That term is came when the thing is or the event observations with respect to light, and then calculating that things. So we'll reach here the redshift which is given by in terms of the scale factor. So this equation means a lot to the one phenomena of the cosmology which is known as expansion of universe or expanding universe. So here my topic I have taken modified gravity and its cosmological implications. So that is one phenomena of the evolution of universe is expanding universe, and that sorry, and that can be explained very well with respect to the modified gravity framework. So we are focusing on this expansion of universe, and then I'll come back to the cosmological model in framework of it. So with the expansion of universe, the parameters redshift and the scale factor that has that plays very vital role, and this is the relation between the redshift and scale factor. Okay, and this is known as the some formula and so on. So now in curvature, but finite and unbounded with respect to the curvature, positive curvature value. Universe can expand or contract. It is overall scale factor is not constant. So this term, this scale factor is not constant. And then universe expands, contract, radiation emitted, and how the ingredients of universe also varies with respect to the evolution, when it is expanding, when it is earlier, when it is not expansion as not expanding accelerated way. So how the ingredients or matter content of the universe varies, that also we can discuss. So now coming to the 20th century, that is birth of observational cosmology. So observational cosmology that gives the idea that the universe is expanding, and that thing starts when the Edwin Hubble uh, s- uh, came, and then he observed the universe through its Hubble's telescope, and that is in 1930. And I think it started so long to reach the conclusion that universe is expanding, and that is a big history behind that, how these things happened and how people are accepting each concept, people are not accepting, and this war is going on for so long. At the end it was came into picture that Hubble's telescope and Hubble's law is naturally expects the universe to expand, but a very things few they accepted and few things and all. But after that, when the expansion eventually is discovered by the observation, so then they accepted that okay, Hubble was right, and that observations it came from what we can say supernova experiments, and all those supernova type A, type 2, anisotropic, CMB, and all those observational experiments came into, and they agree with that concept, and then they accepted it. And now coming to the that is the expanding universe, when the first evidence is 1929 by Edwin Hubble. So what is the Edwin Hubble law discovered? So Hubble discovered the velocity distance relations of galaxies. So how this velocity relation they are related to in the things. So this V is the okay. And now coming to this Hubble's law, when the universe is expanding, so how these things is getting changed. In general relativity, the velocity, and if you are checking, this is, let's say this is the radius of curvature or radius of the things, then how these things is getting changed. So now if you see here, this is the one event, let's say, and when the with respect to time, when it is expanding, then the term is changes to this one, and this is the term is added when it is expanding, and this term which is nothing but the scale factor, and that's the reason when this thing is converted to this scale factor, that's the reason when we are dealing with the Friedman Robertson metric, we are getting that scale factor term, which is the rate of expansion of the universe. Okay, and then if that is the case, then the velocity, it will changes to in this form, that relation, and this h, which is a dot by a, the rate of change of scale factor, which is known as the Hubble parameter, and this whole thing is known as the Hubble's law for expanding universe. Okay, and then the object value of Hubble constant, the object value of Hubble constant, it is given this way, and Hubble, they also found the time and distance, those things they have calculated and all. So basically, when you are coming to the part, as per the content, when we are discussing relativity and cosmology and what are the mathematical backgrounds, and then what are the then how the standard cosmological model came into the picture, and how to deal with that standard cosmological model with respect to another theory of gravity apart from general theory of gravity. So till now we are dealing with general theory of gravity with Hubble's law and Hubble's discoveries for expansion of universe. Now let's do that things in a mathematical way, which is known as the relativistic model, or we can say standard cosmological model. Usually, general relativity allows one to calculate the behavior of space-time in the presence of mass energy. So, when the Einstein came into the when the Einstein came, and before that Newtonian and Maxwell, those things are there. But when Einstein came, what he did, he just wanted to study the geometry of universe along with the matter, and then combinedly is known as the Einstein field equation. Okay. And how that Einstein field equation came into the figure. So the Einstein field equation, usually it is written, let's say Gij equals to uh, 8 pi Tij, and some constants will be there. So this part is known as Einstein tensor, and this left part, so this is known as Einstein field equation. Okay, so in this field equation, the left side is defines the geometry of the universe, and right side it defines the physics of the universe, or you can say the physical matter content, what is present in the universe. Okay, so combinedly, if you study, that is known as Einstein's theory of relativity, or what we are saying the general relativity. And here, when you are dealing with the geometry part, so how the geometry of universe is getting defined, how you are discussing the geometry of the universe. So before going to this geometry, the first key point of this geometry is space-time, space-time metric. Okay, so this metric, which is the space-time interval, or the what is that interval, or what we can say the separation in 2 points in a space. So first we will take the space time. In general, if you say we are taking distance between 2 points in a space time coordinate, or distance between two events in a space time coordinate, how the separations, how the differences occur is there. So first we will take the metric. So let's say that is dA square equals to some matrix, let's say dt square, and then at, as I said, when we are dealing with the expanding universe, we have to keep this scale factor and the space coordinate times. So first we are taking the space time metric. So this one is okay, and this space time matrix has a scale factor which defines whether is rate of the expansion of the universe. Then in that two event, this is the metric, or we know that in topology we are talking about metric. What is that metric? It is distance between 2 points, right? Here also in the same concept, it's saying space-time matrix means you are taking the separation between two events on a space-time coordinate, and how those things is getting affected. So now, second, after this space-time matrix, there will be another term known as Christoffel symbol, or we can say the connection, means how these two events are connected in that space-time, that will be defined by the Christoffel symbol. And this symbol is sometimes written in this notation. And if we see it is very carefully, the representation of this Christoffel symbol and these connections, it is completely from our tensor calculus, it is a mixed tensor. Okay, so this is covariant and this is contravariant indices, we can say, and this completely Christoffel symbol and space-time metric tensor, all those things are mathematically can be calculated by using tensor calculations and differential geometry. Okay. So after calculating these things, then we will come to the another component known as also a second rank tensor, and that can be calculated from by using the tensor algebra or tensor analysis, how tensor getting calculated and all that properties and all. So this curvature, or you can say Ricci tensor, and this is also sometimes known as Ricci curvature. So what it defines how how a volume in a curved space differ from a volume in Euclidean space, means how much curve is there in the space time. So I forgot to say, when you are dealing with this general relativity and the Einstein field equation, that is what I have shown here, 8ij equals to 8 pi Tij. So what this whole equation tells us? The whole equation tells us, so if suppose we are taking this space, and this is, we are putting a some mass here, and then it says matter tells to geometry how to curve, and geometry tells the matter how to move. In that case, in that statement, if you say, so first things, how much curveness is there, that means matter suppose tells the surface how to curve. So this curveness, it can be analyzed through using this curvature tensor or Ricci curvature. Okay, so now taking the trace, doing some manipulation and tensor analysis, we will reach to the tensor known as Einstein tensor, and which is the left part of completely geometry of the universe. After finding the geometry, then we have to go for this matter component, and which matter is responsible for this expanding universe, and when the universe is expanding, how the matter is behaves and how the matter available at that time, and so on, right? So when we will come to that part, okay, so that is what the things we are discussed there. Now coming to this model. So first, as I said, calculate the behavior of the space time in the presence of mass energy. So if you see here, in the presence of this mass energy, how the geometry is getting changed, and how the space time, how the space time behaved, and how the matter, if you are throwing something, how it is behaves and all. So that is what the dealing with the relativistic model means, or general relativity what says, and what is the real meaning of Einstein field equations. So using that things in presence of mass energy, so let's say this is the expanding or contracting, and we are taking this equation, and then simplifying all that things, so we'll reach here equation. And this equation, if you see this component, if it is always positive, so universe expands forever. If it is 0, then universe expands at decreasing rate, and if it is less than 0, then it is expansion reverses. And how this parameter, how this term is affecting the things. So here we are saying it is, you are dealing with the, let's say it is a spherical coordinate, and so on. So and then replace the another point, when you are coming to this relativistic model, and then later on when you are modifying slowly, and then we are coming the relativistic form, and then this term is represented to the curvature. And the curvature, this is basically when you are dealing with the mass energy curvature of space time along with the mass energy relation. Now let's what we'll do, this mass energy of the universe will represent with the matter component, because in Einstein field equations we are attaching the matter component into the field equation. So when the matter is there, how the mass energy and matter will combine, then we will go for the energy and momentum together. So after that, it will be modified the equations and in the relativistic form, and then it will come into the curvature part, and then the mass density or energy density, it will be replaced in this form, means this one it will be replaced in this form. And then it will be the r0, what can the present radius of curvature, and how these things is coming. Now coming to the completely modified form of the field equation, that is what I have told here, Gi is equal to 8 pi aj. Now coming to the completely mathematical formulations. First one is Friedman equations. So Friedman equations is derived from the Einstein equation. This is the Einstein equation. And this left side, which is known as the Einstein tensor, and this one is known as the curvature tensor, and this part is matter component, and the matter component is defined through the energy momentum tensor. So this one is energy momentum tensor, and this one is curvature tensor, and this all together is known as the Einstein tensor, or we can write Gij. So now we came into this field equation, where the Einstein about to say that we have to study the what is the geometry and matter, geometry and physics together, or we can say the geometry of the universe and matter content in the universe. So now, and this is the Friedman equations we derived from that, this equation, and where the density is given by this term, so we can write here rho is the energy density. Now to solve this Friedman equation, this equation, and h, as I said, this is the scale factor term, a dot by a, which we have also here. This is the h, and here, and see here, when we are dealing with this k, so when the k is here, I think we have discussed this, when the k is 0, we are saying is flat, when k is minus, it is open. I think we have discussed somewhere here. When is k 0, then we will go for the flat universe. So just that part. So where we are, yeah. Okay, so as I said, to observe this geometry, to observe this part, when we are dealing with this equation, we must know energy density involve as the universe expands. So how the energy density evolves as the universe expands? So these things we must know, and we must observe how the things, which is the main cause of the expansion of universe. What is the main reason for the expansion of universe? And that can be observed through how the energy density, because here the energy density and this energy momentum tensor completely represents the presence of matter components in the universe. So how these things evolves expansion of the universe? So now coming to this cosmic inventory, if we see the universe filled with 4 different types of energy. So if we see that, and then some radiation, which is photon and neutrons, dark matter, and we can say the baryonic matters, known energy, and there is a large amount which is form of energy, and that we named as dark energy, because we don't know it, it is completely dark. Okay, so and the presence of this part may be shows that the universe is expanding. Okay, so we need to determine how each component expands evolves and sources the expansion of universe. So how these things are happening? Now coming to the fluid equation. Because when you say here how energy density evolves, university expands. So these are the things what is there and how they are evolve. That evolution can be defined from the fluid equation. So let's say if you see these things, fluid, and the first law of thermodynamics says this is the first Q, it will be the heat flow will 0 when the homogenate is there, because initially we say the space time is or universe is homogeneous equation will be in this form. So now coming to the fluid equations, when you are using this term and then you are taking the volume, then this equation will be converted into this form, where this is the scale factor, and also this is known as the fluid equation, or we can, and this can be derived from the Friedman equation too. So using this fluid equation, now the cosmological fluid will are described by a constant. So the thing is, this is the fluid equation in general. Now we can categorize the fluid. How the fluid can be getting categorized? So that can be defined with the relation between pressure and energy density of the universe. So this relation pressure and energy density is its term as the equation of state. So this equation of state, it will describe the fluid. That means when the fluid is in matter era, when the fluid comes to the radiation, and so on. So now using this term, and then the fluid equation can be converted into this fluid equation will be reduces to this form. So now the thing is, if we simplify it, if we solve it, now we can see these things can be solved by using simple differential equations. As I told, when the mathematics we are using to define the geometry part, we are using differential geometry and tensor calculus and so on. And when you are coming to the physics part or governing equations and evolution part, then we have to take the help of differential equations. So now if you simply just do the integration both the sides, then we will get the solution will be looks like this. So now the density is proportional to the scale factor. And then when we are saying the matter, means when the universe is filled with matter, so that means the pressureless fluid. Okay, and then the matter density, so when p equals to 0, then it will goes to in this form. So look at here, when p equals to 0, then the omega will goes to 0. This is your equation of state, and if omega equals to 0, then rho will be directly proportional to the a to the power minus q. So the most of the matter in the universe is non-luminous dark matter. So ordinary matter is very less than 5%. So when the universe filled with, when the universe is filled with matter, which is like ordinary matter less than 5 point, then the energy density will be proportional to the a to the power minus q. So basically, when the matter content, or when the universe filled with the matter like ordinary matter less than 5%, then the energy density evolves with the scale factor in this relation. So now these things, if you put into the Friedman equation, then we'll find the solution. Then we'll find the solution which will be a is the scale factor, because look, in this space-time matrix, usually we are looking to find the scale factor, which is the unknown term here. Okay, so which is the unknown term, the things we can find those things. So now we found the solution in terms of time coordinate, that is a is directly proportional to t to the power 2 by 3. Now similarly, when the relativistic fluid is in form of the radiation era, then the omega it will be 1 by 3, and then rho will be directly proportional to a to the power minus 4. And then these things, the radiation of the universe are photons from the early universe, and that can be detected through the cosmic microwave background. Now using that relation, if you put, then we found the solution of the Friedman equation is a to the power t half. So this is how, when it is matter and when it is radiation, how the solution of Friedman equation is getting derived. then we are taking together those things, this is how it will be coming into the picture. So now the thing is, till now we are dealing with the Friedman equation. Now acceleration equation. So what is this acceleration equation? So acceleration equation is combining the Friedman equation and fluid equation. So this is the Friedman equation and this is the fluid equation. So now if you combine, then we got the acceleration equation. So this acceleration equation will give when the inverse is expanding, when the inverse is not expanding. So there are two different cases. So when P is, so look at here, when the P greater than minus 1 by rho in this case. So what will happen in this left side? So if P greater than rho, then this whole term it will be negative. Yes or no? So this right side part it will be negative. So it's basically when these things will happen, when P is greater than minus 1 by 3 rho, so then the whole right side it will be negative. Okay, and the negative, then this part, if this part is negative, then our A double dot it will be less than 0. Okay, so what it will represents, if it is, if in this case the expansion slows down, and when P less than this value, mostly from this, then the expansion will speed up. So usually the scale factor, when it is positive, then only it will shows the inverse is expanding. So when this situation will happen in our fluid component or matter component in the universe, then the geometry of universe will give you the expanding universe. So this is what the form or acceleration equation tells about when the matter components have this relation, means the pressure and density, then the geometry of universe will give you the expansion speed up. So when this situation will happen, in which era? Initially, when we have done this matter, it is goes like in a power law, it's expanding in a slow process, and when you are coming to the radiation, it is also going to the radiation era. So there are three stages of the universe now. Initially it was matter dominated, then radiation dominated, now it is expanding universe. So how this expansion of universe is happening, and which is the dominated component for that expansion universe, or we can say which is the uh, leading component, or which is the major issue for this. So now we are talking about this matter era, what we can say, like things. Now this part, now this is the part when the universe is accelerating. So now in this page the universe is accelerating, what we have derived from the acceleration equation. So now we have to find out how this dark energy can lead to the expansion of universe. Okay, so people believe that in this page our universe is accelerating. So maybe there is some energy, hypothetical form of energy, because we don't know it, then that is how we are named it dark energy, and then main cause of this expansion of universe. Okay, so in that case where the density component will be related to the pressure component in this form, and the universe expansion will speed up. So this is the era or when the universe is dominated by dark energy. Okay, so 1998 it was discovered that the universe is accelerating, means the expansion is very high, accelerated way. And then the source of this acceleration is unknown, because we don't know. So we just named it as dark energy. It's not like that part is dark energy part, because we don't know that name, that's why we gave the name is dark energy. Okay, and how the observations in happen, that supernova and distance modulus and all. So these are the observatory, and the output is like with dark energy it is expanding, without dark energy, and how these things is come. This is the observational evidence of universe expansion of universe in a accelerated way. So now and again, to define that dark energy, the simplest form of dark energy is cosmological constant. Okay, so using that cosmological constant, then we can say whether the universe is expanding or not. So this cosmological constant can be included in the left side of the Einstein field equation. So when Einstein field equation Einstein derived, that time he kept one constant just to balance the equation. Later on, and then the controversy came that it was not true. He himself also told this is the biggest blunder of the life, something like that. But later on, when the people study more and all in accelerate, then it plays the vital role to represents or explain the accelerating expansion of universe. And the simplest form of that, it is cosmological constant. So moving this term to RHS, it becomes the vacuum energy, as we can say. So now if you see, if you take this form, and then this is constant, and then reading the thing is, when it is coming to this part, and then you got this one where omega is -1. Okay, when omega is -1, then the scale factor and the Friedman equation, it will give you these things. And then we found the solution, scale factor, which is exponential. That means it is uh, accelerating expansion, and which is exponentially accelerating. So now the thing is, this exponentially, we are solving differential equations, and we are finding the solutions, whether it is a powerless solution, whether it is a exponential solution. Then this is the how the inverse phases, so on. So first one is like radiation era, and then coming into the matter era, and then it is in dark energy era. So this is the current phase what we are staying now. Okay, so this is the one part we are dealing with the dark energy, and we are saying the universe is expanding, right? So without implementing dark energy, how we can show the universe is expanding? That is the main catch here. Without showing the presence of dark energy, how we can say that in theoretically that the universe is expanding? So what we will do here, okay. So without representing dark energy, or without taking the dark energy into the picture, we'll say the universe is expanding theoretically. So that can be possible. What we'll do, if we'll if we'll modify the Einstein field equation in GR. If we'll modify the Einstein field equation in GR, then we can see we can see the expansion of universe without implementing dark energy. So that thing, when that kind of thing came, then the modified gravity theory came into the picture. Okay, so the modified gravity theory, when the dark energy cosmological model characterized to the equation of state parameter, and then we can say this is the pressure and density of the fluid. Okay, why this modification requires? I told that is the main requirement, that one of them is what is that, study for the expansion of universe, we need to study, or we need to find the alternative ways to study the expansion of universe without implementing dark energy. That is needed for, that is the main cause for the modified gravity. Apart from that also, there are some other problems. We can say the horizon problem, singularity problem, which I am not defining here. Some places the Einstein general relativity fails to explain that things. So in that case, it is required to modify the theory and required to avoid that problem. We required to solve that problems. So it is required to do some alternative theories of gravity, so that we can overcome those issues for like flatness issues, singularities, and so many things are there. So when GR does not provide the sufficient ideas to solve this kind of issues, then the several modified theories are introduced in the literature to study the behavior of accelerating universe, and so on. So how this modification occurs? So modification were made in the gravitational part of Einstein Hilbert action, or the other hand, the matter part of modification in Einstein-Hilbert action. Means when we have taken the theory, either we can only this part we have to do the modification, so that will lead this Quinten's Chaplin gas and holographic dark energy and so on. When we are dealing only the matter part modification. So when we will do the Einstein-Hilbert action, then the whole equation will get changed. When we will change the action, then whole equation will change. So now I'll go to one of the published work here, how this modification occurred in the Hilbert action and how we are dealing with the cosmological model to study the behavior of the universe. So I'll just take one of this published paper. Okay. Yeah. So this is one paper is published. So periodic cosmic evolution in FQ gravity theory. So this FQ gravity, which is the modified gravity theory. So how this modified gravity is coming into the picture. Some formulation of FQ theory. Okay, so this is the what we can the mathematical formulations, but how it came into the picture. So when will came into this action? So this is known as Einstein-Hilbert action. So when you are dealing with GR, so this part, instead of any arbitrary function of scalar terms or any arbitrary function of curvature term, if we take only Ricci scalar, then that will give you to the GR equation. If we modify here some value, then it will give you the modified gravity field equation. And if we convert, this is the matter part, we can say, if you convert some matter component, then it will give you some other alternative theories. So if you do some modifications here, instead of using only Ricci scalar, if we will use the arbitrary function of curvatures, then it will give you the different alternative gravity theories, like you can say f of r gravity, f of rt gravity, and so on. So here we have taken one Terson scalar. Let's say this is one kind of modified gravity. So now how these things? So if you vary this action, then it will give you the governing field equation. Let's say this is the governing field equation. Okay. So what we'll do in this field equation, we need to put the geometric part. So the geometric part means we have to calculate the Einstein tensor, and then we have to take the fluid component, which is behaves the matter present in the universe. So here we have taken the space-time metric because we have to discuss the left side of the Einstein field equations or governing field equations, and that can the key point is space-time metric. So we have taken here in Cartesian coordinate we have taken FRLW metric where A is the scale factor, and one more point here, sometimes if you see here minus can be here or here, so it is conveniential because we say it is the signature of the matrix. So signature of the matrix means suppose if you are taking suppose dA square equals to dt square minus dx square dy square dz square, then it will give you plus minus minus minus. So if you do, it is known as minus 2 signature. Similarly, if you put minus here and all these things plus, then that will give you minus plus plus plus. So it is plus 2 signature. So sometimes it can be taken plus 2 signature and sometimes can be taken minus 2 signature. So here we have taken plus 2 signature. That means 1 minus and 3 plus. And this is yes flat space time FRLW space time. Again, after taking this space time, so using the connection and Ricci curvature, we will derive the Einstein tensor. And then we have to take the matter components. Let's say it is, we have taken perfect fluid and where the pressure density is related with each other by using the equation of state parameter, let's say omega. So we have taken the space-time matrix for derive the geometry, and then we taken the fluid of or in the form of energy momentum tensor, because the mass energy it will be converted into the energy momentum tensor when you are dealing with the relativistic model. So we have taken here the perfect fluid which will be given in this form. Now using this matter and this metric, we have derived the governing equation here. Okay, so this governing equation, we can say the modified Einstein field equation in the framework of FQ gravity. So FQ, which is one of the modified gravity here. So what we'll do here? So here we have two equations, right? So in these two equations, how many unknowns it will be? We don't know the value of rho, we don't know the value of P, and we don't know the value of H. Okay. So now if you see this equation very carefully, which is nothing but a system of partial differential equations, and where a system is not consistent, that means the number of equation is less than the number of unknowns. So we know when we are dealing with the matrix theory or solution of the by using matrix method, or when we are dealing with the system of equations, we must know the system should be consistent. That means the number, if you want to find the exact unique solution, then the number of unknowns should be, this is the common mathematical things. Suppose if you have a system of equation and the number of unknown and number of equation. Okay, so let's say the number of equation is m and number of unknown is n. So if m equals to n, then we will get unique solution, right? And when the number of, if n less than m, so what will happen? If n less than m, that means the number of unknown is less than the number of equation, then we will get the no solution. And if m less than n means the number of equation is less than the number of unknown, then we will find the infinite many solutions, right? So here what we'll do in this case, we are not going to find the infinite many solutions. We'll make it consistent, means number of equation equals to number of unknown. So to make it consistent, what we'll do here, how to solve this nonlinear system of equations, we will assume some ad hoc physical conditions, and that conditions should be related with these unknown parameters, So basically in differential equation, when you are solving a known solution and using that known solution, we are finding the another solution which is known as the method of variation something. Similarly here also we'll do in that same format. So what we'll do, we'll assume a physically reliable ad hoc assumption, and then we'll make the equation should be consistent, right? So when we will make the consistency, then we will find a unique exact solution to this differential equation. So now the point is how to do that assumption. Now we have studied that the relativistic parameter, which is Hubble parameter. Okay, so the Hubble parameter can be parameterized into different cosmological parameters. Let's say deceleration parameter, and also the Hubble parameter can be written in terms of scale factor. Okay, so when the Hubble parameter is parameterized in form of deceleration parameter, so deceleration parameter, it is defines how the inverse is, when the inverse is accelerating, when the inverse is decelerating. So scale factor, it gives the rate of acceleration, a rate of expansion, and q, that is the deceleration parameter, which defines whether the inverse is accelerating, decelerating, and how the expansion is behaves. So what we'll do here, okay, so now here we have taken one form of this deceleration parameter, that is known as the parameterization process to find the solution of this equation. So the parameterization process means we have to take one parameter which must be, when you are taking the physically reliable ad hoc condition, and that relation or that condition must be related to one of these parameters. So what we have taken here, we have taken the deceleration parameter which is related to the unknown parameter h. So which is related to the unknown parameter h. So to verify that whether this reliable or not, that also we need to check. So So here we have taken the assumption on this deceleration parameter. So if you are assuming the deceleration parameter, then what will happen? One known trial solution will implement here, and then our system is consistent now to find the other unknowns. Means will have two equations with two unknowns now. To take, let's y equals to e to the power mx, that is the trial solution method, and then we are using that solution, and then we are finding the other actual solutions of the differential equation. So similarly here also what we'll do, we'll assume this ad hoc condition, means we'll take this deceleration parameter as the trial solution, and then we'll implement that things, and then we'll find the other
That
values. Yes, sorry. Okay, so then we'll find the other things. So now here we have implemented the deceleration parameter known as one form, which is periodic varying deceleration parameter. Okay, so here two parameters are there, and if you are taking this deceleration parameter, how the Hubble parameter will be given. So corresponding to this deceleration, Hubble parameter is given here. Now what deceleration parameter we have obtained, then how this geometrical structure of this deceleration parameter, and how this deceleration parameter is observationally fit uh, to take this assumption, and how the Hubble parameter will be derived by using this deceleration parameter, and then how the Hubble parameter behaves here. If you are taking periodic varying deceleration parameter, how the scale factor and Hubble parameter behave here, then we can represent that things in graphically. So using that deceleration parameter, we have taken the scale factor, and then using those deceleration parameter value, and with a form of the modified gravity in FQ gravity form, then we have obtained this is the solution of density and pressure. Now, after finding this density and pressure, we have to define the dynamical properties of the means when you accelerating, or when inverse is power, giving the power loss solution. So here we have solutions of density and pressure. Then how the dynamics, so the dynamic properties of the model. So for dynamic properties, first we have to see the equation of state parameter value, because here we have found pressure and density. So if using that pressure and density relation here, we will found the parameter equation of state parameter, whether the universe is dominated by dark energy or not. So here we found this is the equation of state parameter. Now we are taking the different cases of this model parameter, let's say n, which is came from here. So using that parameter and different cases while studying, then these are the evolution of universe you can study graphically. Now we came, since we have taken the deceleration parameter is periodically, so how the universe and how the matter components are behaves, what we can say, yeah, how that behaves periodically, means it is coming and then go on so on. And then another component to study, which is energy condition. Energy condition that will defines through the completely matter part or physics part of the universe. So each cosmological model must be has one paragraph or one part which is defines the energy condition. So energy condition, it represents the attractive nature of the gravity. So it is three types of energy conditions are there, like strong energy condition, weak energy conditions, and null energy conditions, and each energy condition has different features to that. If strong energy condition, it will define whether the universe is accelerating or decelerating, and then weak energy conservations, and this dominant, it is behaves the stabilizing the model, and weak energy, it is used to focus the energy conservation. because we are balancing the geometry and matter component together. So this is the main part to discuss in a cosmological model. So using that energy conditions, so we have found here and all. So now the thing is, okay, so these are the basic model parameters what we can take in here. Now coming to this canonical properties means, the geometry part we have to check more. The deceleration parameter what we have taken, whether it is physically reliable or not, and how it is behaves in a geometric part. So for that we should find out the distance means like diameter distance, and then the luminosity distance which is the observationally things. So if you see that deceleration parameter and then observationally with the error plot with the distance modulation of supernova type air data, then we found here that deceleration parameter which we have taken, it is observationally acceptable, and it can define the physically reliable cosmological model. And then okay, so it can explain the behavior. So basically coming into the part that when we don't have the dark energy component, apart from this there will be some places where we can use dark energy in combined form of other energies like string theory, or we can take bulk viscous fluid. So there are different fluids we can take, and then we can explain the expansion of the universe. And this is one I have shown like in FQ gravity. Similarly there is a few other modified gravities like f of r gravity, f of rt gravity, and so on. So these are the modified gravities where we can use to explain the expansion of universe. And apart from that also other relativistic or astrophysical objects also we can discuss in form of modified gravity. So the thing is the completely model or completely things, it is based on the mathematical structure. Okay, so first thing is, the first part as I said, we are dealing with the differential geometry part where mostly we are discussing the how the curved space time occurs and how these things are there. And then after that, after doing the differential geometry and tensor calculus, then we'll reach to the governing equation which is nothing but to solve the mathematical differential equations which will be highly nonlinear. And the thing is we'll get the field equations where which is always inconsistent, mostly in this instant field equations in a alternative gravity. So then we can take the mathematical help like formulations which is known as the Adduck assumption, or which must be physically reliable. Then using that assumption, then we found the solution to equations, and then we have to study the dynamic of the universe, and then we have to see the physical behavior universe. As I said, when you are dealing with this uh, era also, then if in that case when you are dealing with this dark energy era, it is sure that it can be represented in this cosmological constant called lambda. Then if your if your model cosmological model you are finding, and then if you are comparing with the lambda cdm model, okay, then also you can say that your cosmological model, the mathematical formation of the evolution of universe is physically reliable, and it is it will show the expansion, or it will show that your model when the evolution of universe is physically reliable. So this is one part, and another part is that when you are dealing with the parameter, let's say equation of parameter, so this parameter also gives you the idea about this dark energy era, and it defines this dark energy era into three phases. So when it is less than when is this less than 0, and when it is -1, and when it is uh, less than -1. So when it is less than 0, this phase is known as quintessence phase, and when it is and this line is known as the phantom divide line, and this phase is known as the phantom phase. So this phantom divide line which is -1. So basically this is the universe which is expanding, but when it is coming to this part, it is highly expanding, or we can say accelerated expansion phase. So when the universe or the matter component of the universe filled with phantom fluid, and that phantom fluid, it can be observed, or it can be uh, clarify, or it can be characterized through less than -1. And this is the phantom divide line, we can say. And here we can say the cosmological constant value is here. So when in this phase, it is known as the what we can say accelerated phase, or the dark energy behaves as a, or we can say the phantom fluid, dark energy, and the whole part is accelerated expansion era, we can say, and when the universe is filled with the phantom fluid. Now there will be another part when the universe is expanding. Okay, so it is not like that universe will expand very well. Always universe will expand. It's not like that universe will expand always. Sometimes what will happen after, suppose universe is going and going, after some, in a finite time, it will get some sudden jerk. Okay, it will get some sudden jerk, and then again it will start. So this sudden jerk and this kind of things, it is known as the singularity problem. That means, so when there is a some space time, and suppose there is a in mathematics, if you say, suppose there is a continuous function and something, some places where the derivative does not exist, then, or if you say, let's say it is function and 1 by x, so that means this function does not exist at 0. So what will say, this function has the singularity at x equals to 0. Okay. Similarly, when in the space-time geometry, some point where the things is, the scale factor suddenly goes to infinity or some value, then this place where the sudden jerk is there. So this part is known as the singularity. And when after expansion of the universe, if some places it is the sudden jerk is happening, then that is known as the big rip singularity, or we can say singularity at a finite time in expanding universe. But initially, if you see, initially there is nothing. It started from the zero and started from the nothing. So this initial singularity, what we can say, that is known as the Big Bang or initial part. So this part also it can be observed, because it's not like that only we'll just study that universe is expanding, no. So sometimes what is happening after some time, that also a part we can studying. If there is some sudden jerk is coming, then how to deal with that uh, property, or it is singularity properties, and so on. After from that, in that thing, uh, there is a another hypothetical term in the space-time geometry, when we are saying wormhole geometry, and which is nothing but the quasi solution. So quasi solution to the Einstein field equation, and that is the first exact solution. So in that case, when you are saying this wormhole, so let me to show that one. 1 minute. I'll just stop and then I'll come. Okay. So when it is coming to this part, we're saying normal geometry. I'll just show here. Okay, here also we can see how the action is changed, and then this is what the arbitrary function of Ricci tensor, sorry, trace energy tensor and scalar. So now coming to this normal solution. So this is what the normal metric and known as the square style metric. So the thing is, uh, to make it big one. Okay. So the thing is, this is also one space-time solution, a square style coordinate, and this solution is known as the first exact solution, tail solution. And this solution means this space-time matrix defines the wormhole geometry of the universe. So how this wormhole geometry it will be looks like in this form, you can say it is, and this part is known as the throat of the wormhole. So this solution means when you are dealing with this space-time matrix, if you consider this space-time matrix, this space-time matrix represents the universe in this form, or we can say this is known as the normal geometry. So when you are dealing this geometry, then what is the thing here? We have to see this is we will fix the geometry here, and then we will find out which matter component is responsible for this kind of geometry. Usually what we used to do in general relativity, we have studied the thing, it's like matter geometry together, then how matter behaves for geometry, and in present of that matter component, for that matter component, how will the solution of the field equation, or how is the solution changes. Means how the in modified what we have found here in space time, we found the scale factor. Okay, so in presence of this matter component, how the scale factor, how the solution were behaving, and how the geometry is behaving. Here normal solution what will do, we'll fix the geometry, then we'll find which matter component is responsible. What will happen? So then we'll see here, this is the normal geometry, and usually whatever the things is happening, we are focusing on this throat. Okay, so this construction of ormol geometry and when the energy conditions is violated, and then so on so on. So what we'll do here, we were exactly finding the region presence of, so basically ormol is the connection bridge from two space time, whether it is in a one universe or some separate universe. If you are doing the connection of two space time, then in this part, this throat is known as the ormol radius. And what is the thing is there, so if we'll make a traversable wormhole here, means from here you can enter to here, then you can easily come. In that case, this passage has to be make it clear and traversable. So what we'll do, we'll just study in those things in the framework modified gravity or mathematical model we'll construct, and that mathematical model, when we'll choose the fluid, so we have to find out which matter fluid is present here to make it more traversable. So when you are dealing with modified gravity, we have to and this traversable region is exotic matter, which is negative energy, and but will not accept the negative energy. So it is, we want to avoid that exotic matter. So in that case, we can check the fluid. So to make it is traversable, so to make it is traversable, the fluid can be a phantom fluid. So what we can say, it is known as the phantom wormhole. That means the throat is completely filled with the phantom. Now there will be a small question. What is this wormhole actually? It is basically, if you see in general, if it is closed here, you will have the event horizon. Then this part can be behave as black hole, and this part can behave as white hole. So everything and white hole which is disturbing everything, and white hole which is disturbing everything. everything. So if you together combine and remove the event horizon, then it will be a or more. So there also we can use the modified gravity, make it traversable. So basically, and also I told when we are talking about this happen. So here in this case, I'll explaining here means how the sudden jerk is happening. So look at here, we have the that means when the exponential term. So here we found the solution is in a exponential term. So that means the universe is accelerated expansion is happening. So when these things is happening, so what will happen in the universe after a finite time? So if you see the Hubble parameter, this first part, this part we can say the initial singularity or Big Bang. But when it is coming after some time, again we are getting the sudden jerk. Means it is goes to the infinity. Similarly, if you take that behavior in the other components, let's say density, pressures, and the energy conditions, so we'll face the same issue. So after finite time, this sudden jerk is happening. And this is known as the Big Rip singularity. And we can say the finite time singularity. That means after some finite time, it will goes to this sudden jerk. And this singularity may happen. So this is how the behavior happening in the geometry of the universe when it is just expanding and after finite time what else in that framework. So basically if you see here, all the calculations with the physics. So we can say it is a one of the most widely used applied mathematics part, which is no part of the applied mathematics known as relativity and cosmology. So people, I don't know whether you feel it is more physics and all, but no. If you see the basic part, I didn't I could not go more on the mathematics part because it is completely mathematics. As I told, these are the topics. All together, if you apply, then you will reach the solution or output. It is known as the statistics. So in that, there is so many things are there. I didn't touch the statistical part because, yeah, if when you are doing the observational cosmology, there we will go for the so till in basic, in general, these things we have to take. I again in the Lie algebra when you are dealing with the metric. So this paper so this bank topics like different and the scale factors are different as per the direction. Sorry, in this paper, yeah. So in that case, how the things is happening and bank type metrics. So all that metrics is derived can be the space-time matrix formation also depend in the Lie algebra. And then the governing field equation, that is completely differential equations, and how we are solving a system of differential equation and how to find the solution. So that is the application of that. And then if you are going to the observational part, then we can use the statistics. In statistics we must use the estimations. So now recently there is a software software tool is there, known as Python and all data analysis part. So there what we used to do, statistics part, for first part is descriptive statistics, and then that mathematics what we have to do, and then we will go for the inferential statistics. So here we will go for this observational inferential statistics initials, like we will do. And then another part is that inferential statistics that will do the parameter estimations. So here when you are using the cosmology, like the deceleration parameter, scale parameter, Hubble parameter, we'll get the more number of parameters. Okay, so using that parameter we'll estimate the value, or we'll estimate the model parameters. So here in statistics, what we used to do, we used to do that mean, sigma, like standard deviation. These are the parameters, and then we used to do the estimation on that. Similarly, we can do here. We'll take the model parameters like scale factor, Hubble parameter, deceleration parameter, and apart from that, there is some density parameter and so on. So using that parameter, we can do the parameter estimations to see whether the model is observationally or not. At that time, there is some observation data will be available, like supernova data and CMB, BAO. There are so many observational data are there. So when you are constructing the cosmological model, whether your model is not, that can be cross-checked through the mathematics called statistics. And then that parameter estimation, sometimes if you are not able to do analytically, then you can go for the numerical simulations. So these are the basic mathematics we're using, or you can say this is the part of the applied mathematics. And when you are all together, if you use, and then one output it will come, which is known as the cosmology or relativity and cosmology. But when you are represent with language, that language we can say in physics language. That is what we can say. And this part of this applied mathematics is widely used, not only in mostly in India. They are thinking that it is part of physics, but it is not. If you see some outside, there will be a particular so many centers for theoretical physics. So that theoretical physics is nothing but the applied mathematics part. Mostly when you are doing all those things here using this mathematics, then what output you will get, that is what your theoretical physics. And it is very important to do the things like what observation we are doing today. They may not be same for the next future, but if we have some theoretical evidence, then the next future generation should go through that theoretical evidence. Yes, these things happened and these things are there, so we can do the more. So it is important to do the theoretical part, or important to construct the theoretical evidence to do the future observations and experiments. So here we cannot do experiments because we are staying inside the same universe, so only we can observe through the event. So in simple example we can say, if you just ask to a small kid or school kid or some inter kid and all, they all are familiar with the Einstein, but they might have not known about the Hubble, because Hubble did the experimental part, observational part, right? But the theoretical evidence is given by the Einstein. So people are very familiar with the Einstein more than the Hubble. Those who are coming to this topics and all, they are known that okay, Hubble is some scientist, one of the scientists who did some observation, but they are all known with the Einstein relativity. Okay, so in that case we must have the theoretical evidence, and that theoretical evidence of all observational, like physical observations and all, that can be done by the mathematical people, because physics people they don't do the more mathematics part. So we mathematicians will act as a helping verb to those physical people, so that later on they will get more benefits to do the more extra observations through the theoretical evidence provided by the applied mathematics people. So I hope it is little bit clear to all of you. So I'll stop here and I'll expect some discussions and questions. I hope I'm little bit reachable to others. I don't know. So please. Yes. Okay. Yes, I'm here. Yes, yes, yes. Uh, Customer. Thank you so much. Have a good day. Okay, I think I have completed little early. I thought discussion will be there. Dear participants here. Thank you. So, okay. So have a good lunch today and enjoy the next session. I think it will start from 1:30, right? Okay. Sure, sure. Is the same link for the next session? Okay. Thank you. So can I leave now? Uh, Indrayani ma'am is there? Hello, am I audible? Hello, sir. Okay. Yes, Indrayani ma'am is hear me? Okay. I don't. I think it's okay. But I think I might met her somewhere. That's why I just asked. It's okay. So, is there any things to do? So, can I leave now? Yes, I think I met you somewhere. I don't know. Have you came to Latur? I think 2018 or 17. Uh, okay. I just see the face, familiar face, so it's okay. Okay, ma'am. Can I leave now? Okay. Thank you so much, and thank you everyone. So hope to see you again somewhere at healthy lunch. So thank you all. Yeah.